So we just learned the word amphoteric, right? Water is amphoteric. It can act as an acid or a base. It can accept a proton or donate a proton. Autoionization is the process by which water can do this. So autoionization, it's ionizing with itself. So that's this reaction over here. Here you have a water molecule and another water molecule. This one can act as the acid by donating a proton to the other one. This one acts as the base. So then this one becomes the conjugate acid, and that one becomes the conjugate base. Yeah? Yeah, so how does this work out, right? And the question I was just going to ask you is, why would water do this, right? Usually when you see things in nature's trying to make everything the same. These guys are the same. Why would they just suddenly become different? Well, they only do it a little teeny tiny bit. They just do it a little teeny tiny bit. So, spoiler alert, the acid, the equilibrium constant for this is 10 to the minus 14. Really, really small. So in a cup of water, you have very few hydrogen and hydroxide ions. It's almost entirely H2O. Does that answer your question? So here we see water acting as an acid, right? It can accept a hydrogen ion, donate a hydrogen ion to the ammonia. Here we see water acting as a base. It can accept a hydrogen ion. So it can do either. And when we have just water, it does this a teeny tiny bit. So here we have this equation written with hydronium. And here we have, this is representing the same thing using H plus instead of hydronium. So we can also think of it as one water molecule losing a hydrogen ion, becoming hydroxide ion. But we know that this hydrogen ion doesn't just go floating around. Did anybody see a newborn baby like on the sidewalk when they came in today? No. They're never out by themselves, right? I mean, worst case scenario, they've been kidnapped, right? Somebody took them, right? But they're still not out there by themselves, right? They're just never out there by themselves. H pluses are never out there by themselves. We sometimes show it in an equation like they are, but we understand, oh, he's too tiny to be out by himself. He's actually sitting on another water molecule. But it makes the equation simpler. Everybody okay with that? So we can write an equilibrium constant for this equilibrium, the expression, and it's going to be H plus times OH minus. We're not going to do anything with the reactant because it's a liquid, and those don't show up in the expression. So we can write this as H plus, or we can write this as H3O plus. They are different representations of the same thing. So this has a subscript W, and this is just for water. It's called the ion product constant for water, because we're looking at ion products. So at 25 degrees Celsius, standard room temperature, Kw is 1 times 10 to the minus 14. So very, very small. In pure water, for every one water molecule that ionizes, you get one each of hydrogen ion and hydroxide ion. So the hydronium ion or hydroxide ion concentration will be equal to the hydroxide ion concentration. Just like if you had a whole bunch of brand new shoes in boxes and you dumped them out, you'd have an equal number of left and right shoes because they were together to start with. And so we could figure out the concentration of that by taking the square root of Kw. Concentration is 1 times 10 to the minus 7. So the concentration of the ions in pure water, very small, 0.00000001, really small. Water is not acidic or basic, it's neutral because those concentrations are equal. Any questions? You did learn about some of this stuff in Chem 3A, but I recognize that might have been a while ago. So what we call an acidic solution is a solution that has an acid in it. You put an acid into a solution, it creates extra H3O plus ions. The ion product constant of water still applies. Let's write that out. So this is at equilibrium, Kw is 10 to the minus 14. What happens to the equilibrium if we add more hydrogen ions? It's going to shift to the left, right? Because the equilibrium is a spoiled child and it doesn't like that you did something to it. So it's going to rebel and try to make it the same. So you add something like HCl, which is going to put extra hydrogen ions into the solution, or hydronium ions, they're the same thing. It shifts this way. What does that do to the hydroxide ion concentration? It goes down. So the hydroxide ion concentration decreases, and the H plus concentration is increased because you added acid to it. Equilibrium shifts towards the reactant. So we have hydronium ion concentration greater than hydroxide ion concentration. That is an acidic solution. A basic solution is the opposite. Here you have a base that created additional hydroxide ions. So here we have our water, and we add something like sodium hydroxide, which has hydroxide ions. What's the equilibrium going to do? It's also going to shift to the left, causing the hydronium ion concentration to decrease. This will be less than its normal 10 to the minus 7. This will be greater. So we have hydroxide ion concentration bigger than hydronium ion concentration. Any questions? So a basic solution has more base in it, and an acidic solution has more acid in it. So here we have 3 solutions, and we're asked which solution is acidic, and they're giving us the hydronium ion concentrations. What's pure water? 10 to the minus 7. That's neutral, right? So neutral is 7, 10 to the minus 7, so this is not acidic. If it's an acidic solution, is the hydronium ion concentration larger than 10 to the minus 7 or smaller? Acidic solution. It's going to have more acid. Okay? Acidic solution, more of the acid. So it's going to be this one, because this is a larger number than that one. This one's neutral. What about this one? It's going to be basic. Questions? Calculate the hydronium ion concentration for each solution, and then determine if it's acidic, basic, or neutral. So we're going to use this, we're going to use the equilibrium constant for water to do this. The equilibrium constant of water is the only equilibrium constant you need to memorize. 10 to the minus 14. So Kw is equal to hydrogen ion concentration times the hydroxide ion concentration. And that's equal to 1.0 times 10 to the minus 14. We learned about this in chapter 16, right? So this is the equilibrium concentration of hydroxide ions. It's asking us what's the equilibrium concentration of the hydrogen ions. Well, we need to plug this into this equation and we'll get the hydrogen ions. This is a situation, especially since we have to do this more than once, where it might be a good idea to rearrange the equation. Divide both sides by hydroxide. Those cancel out. So the hydronium ion or hydrogen ion concentration is 1.0 times 10 to the minus 14 divided by the hydroxide ion concentration. So then here H plus 1.0 times 10 to the minus 14 divided by 1.5 times 10 to the minus 2. My calculator gives me a bunch of zeros. Again, my rule of thumb is if there's more than 3, put it in scientific notation. So if this is the hydroxide ion concentration, did I do that right? No, I didn't. That's wrong. Like, wait a minute. I put 1 times 10 to the minus 7 instead of 14. Why? I don't know. Now I did 11. I'm just going to start over. 1 times 10 to the minus 14 divided by 1.5 times 10 to the minus 2. It's still 6.7, but now it's 10 to the minus 18. You okay with that? That's pretty simple math compared to chapter 16. Is this solution acidic or basic? It's basic. We determine that by looking at which of these is there more of. The hydroxide ion concentration is larger than the hydrogen ion or hydronium ion concentration. Yes?
I'm getting 6.7 times 10 to the negative 13.
Thank you. What is wrong with me? This time I divided by 1.5 times 10 to the 3. It is. It's a Monday. Okay.
Sorry, is it supposed to be 10 to the minus negative 14?
Is what's supposed to be that?
The,
KW?
yeah.
Well, I kind of don't know if I know anything right now, but I believe so, yes. But, I thought I did that one right, too. So, minus 13. Yeah. We got to the negative 33. Interesting. That means that something is happening with your calculator. So this is a problem if you're not using the scientific notation button. So on the top here, 1.0, and this part here is the EE button. Oops, not the minus. Times 10 to the. And then, so that's EE negative 14 divided by 1.5 EE negative 2. And what does that give you? Got it? Okay. So, mistakes you can make there, if you're doing this the hard way and you're doing times 10 raised to the power, and you just do this in a linear fashion, you enter that number, you divide by this number, what your calculator sees is 1 times 10 to the minus 14 divided by 1.5 times 10 to the minus 2. Wrong answer. I also have demonstrated that if you use the wrong numbers to start with, you get the wrong answer. So use the EE button. If you're just like super stubborn, if you use that box over box button here, it will still work. Any questions? Okay. This one, the hydroxide ion concentration is 1 times 10 to the minus 7. Now, we could do a calculation here. But back here, we learned that in pure water, these concentrations are equal, and they are equal to 10 to the minus 7. So do we have to do a calculation there? No, we don't. Did we ever decide if this was acidic or basic? We got sidetracked by all my mistakes. It's going to be basic because hydroxide is higher in concentration. So that one's basic. And this one is what? Neutral. Okay, this one, hydroxide ion concentration, 8.2 times 10 to the minus 10. Take the hydrogen ion concentration is equal to Kw divided by the hydroxide ion concentration. Let's see if I can do it right this time. One 1.2 times 10 to the minus 5. Cool, I got that one right. Acidic or basic? Acidic. The H plus concentration is larger than the hydroxide ion concentration. Okay, show me your thumbs. I got it. I'm confused, totally lost. Awesome. Let's see. That's the one we just did. Okay, pH scale. The concentrations of hydroxide ion and hydronium ion are all pretty small, and they're all over the place. They can go as low as like 10 to the minus 14 up to like 1 or even 10, right? And so you've got all these zeros in there, and it's this huge range. So the pH scale was developed just to make this more compact, and it does that by using logarithms. So the pH is defined as the negative logarithm of H3O+. This is the base 10 log, and this is a negative sign. It is not the anti-log. So that's just type a negative sign. So pH is negative log of H3O+. So here we have a solution of H3O+ being 5.3 times 10 to the minus 8. What's the pH? Well, we're going to use the equation. We're going to try to use the equation. pH equals the negative of the log of that concentration. negative log. On the 36X Pro, there's one button that does natural log and base 10 log, and will also do other logs. And so what you do is you press it twice until it says LOG. That's the log we're looking for. 5.3 EE minus 8, close the parentheses, and I get this number. Any questions about that? Your calculator's cooperating? Let's talk about sig figs. How many significant figures does this concentration have? 2. So we should report our pH with 2 significant figures. But that would mean 2 decimal places. So in a logarithm, only the numbers to the right of the decimal point are significant. The number to the left of the decimal point is directly, didn't mean to do that, is directly related to this number. So what if we had something that's got an H3O plus concentration that is 5.3 times 10 to the minus 2? Well, that's going to have a pH of 1.26. Yes, I did that in my head. What if the hydroxide ion concentration is 5.3 times 10 to the minus 13? And it's 26. Yes.
Why is it a 6? Shouldn't it be an 8?
Yeah. I didn't really want to come today, and this is just proving that I should have just called in sick. Oh my goodness.
Oh.
Thank you. Thank you very much, actually. 8. It kind of takes away from the whole impact of the thing, but. The 5.3 is where the 0.28 comes from. The 7 comes from the negative 8. This 1 comes from negative 2. The 12 comes from negative 13. So the number before the decimal point is really the power of 10. When you take the logarithm of something, you're finding what's the power of 10 that this is equal to. If we do 1 times 10 to the minus 7, what's the negative log of that? 7. What if we have 1.0 times 10 to the minus 9? pH is 9.00. The log of 1 is just 0. It's not raised to any powers of 10. This is negative 7. And we put the negative in front of log here so that instead of saying the pH is negative 7, we say it's positive 7. Here, this concentration, 10 to the minus 9, pH is 9. And so we see with this one that this number is going to be very close. It'll either be the same or 1 less than that. Any questions? Yes? Which one? The 1.28? I took the negative log of this number. Yeah, so the negative log of this because the significant figures are the same, the 5.3, I knew that this was 0.28, just like this one was 0.28. Well, after you guys corrected me. And this number is going to be one less than that. Do you need to be able to do that? Like if you know what this one is, do you need to be able to write the pH for other things that are also 5.3 something? No, absolutely not. I am doing this to help you understand why it's only the decimal places that are the significant figures. I'm not going to try to trick you with this on an exam or at any time, but it's important because if you don't recognize that and you were getting 12.28, you might just write 12 because, well, that's 2 digits, that's 2 sig figs, right? But those are not significant. So with pHs, always write one more than you think and you'll be okay. One more decimal place. Any questions? So here's the pH scale. So a pH of 7 is neutral, and that's where the hydrogen ion concentration is 10 to the minus 7. When the hydrogen ion concentration gets larger, it becomes more acidic, the pH gets smaller. So I know that's kind of one of those backward things, but they didn't want to have negative pHs, I guess. So here, the hydrogen ion concentration is 10 to the negative 1. It's a lot more hydrogen ions than at 10 to the minus 7. Over here, this is a more basic solution. This one, the hydrogen ion concentration would be 10 to the minus 13. So very, very small. This is a basic solution. The POH is the negative log of the hydroxide ion concentration. So these are directly related to each other. A neutral solution, the pH is 7, the POH is also 7. If the pH goes down, the POH goes up. If the pH goes up, the POH goes down. Because one concentration is going up, the other one has to go down. It is possible to have negative pH values when you have a very concentrated acid solution. I don't know that we're going to see that much, but it's possible, just to let you know. Negative concentrations aren't possible, but negative pHs are. Any questions? Negative concentrations are not possible. Negative pHs are possible. Because what if you had a pH of negative 1.5? It's going to be a pretty strong acid, yeah. But that means that the hydrogen hydroxide, yeah, just stop talking now. Well, actually, let's just make it simpler. Let's say 1.0. Well, that means that the hydrogen ion concentration is 10 to the plus 1. So 10 moles per liter. Is that possible? It is. There's one acid that can be 18 molar, right? So very, very concentrated. So you can have negative pHs. I don't know where this came from. Any other questions? Calculate the pH of each solution, indicate whether it's acidic or basic. So, pH is the negative log of the hydrogen ion concentration. Here, they're showing H3O+. I'm lazy, I'm just going to write H+. They represent the same thing, okay? So for the first one, the pH of this is going to be the negative log of 9.5 times 10 to the minus 9. Negative. Push the log button twice. 9.5 times 10 to the minus 9. Eight point 0.22276, and you're like, oh, wait a minute, I don't have to write down all these stupid digits. My concentration had 2 significant figures. That means my pH is going to have 2 decimal places. If you have a hard time remembering that, just write down a couple extra digits. Extra digits are easy to get rid of, but if you don't write down enough, then the only way to find out what those are is to go back and do the whole calculation again. Hydroxide ion, they want the pH. Well, we can't just take the negative log of this. We need the negative log of the hydronium ion concentration. So we would have to calculate that first, which we've already practiced doing. What I'm doing here with the sig figs is that these numbers have 2, and so this would have 2. This isn't a log yet. I'm going to write down 2 extras because that will avoid rounding errors. So first I found the hydrogen ion concentration. And now I can find the pH. .85. I'm going to write down 2 extras because that's what I do. So that's the pH of that one. That's the pH of this one. Are those solutions acidic or basic? They're basic. So there's 2 ways that you could recognize that. You could look at the hydrogen ion concentration. This is less than 10 to the negative 7. This one also less than 10 to the negative 7. So then it's acidic. It's basic. The other way is to compare this to 7. Number higher than 7 means it's basic, and number lower means it's acidic. What if we're given the pH and we want to know the hydrogen ion concentration? That's the equation we have. We need to solve this for the H+. Well, we can divide or multiply both sides by -1, right? Get that out of the way, put that over there. Log is a function. We have to do the inverse function, which is 10 to the x. So the hydrogen ion concentration is going to equal 10 to the negative pH. So they told us the pH. So then we're going to have 10 to the negative 8.37. And yes, your calculator can do that. Its end of the X button is on the same button with the E to the X button. Just press it twice, and then type in negative 8.37. And then this is what my calculator gives me. How many significant figures should this number have? 2, because the pH has 2 places. Well, is this going to be 4.0 times 10 to the minus 9? Do we know what comes after that? Why did the calculator stop there? Because that's how many digits it will display. I mean, you're like, well, you've got more room. Yeah, but it doesn't care. So it's giving you the first one, because that way it can show it to you in decimal notation if you're, got it set to show decimal notation. If it went one digit over, it would say, I can't do decimal, I'll put it in scientific notation, because that's the only thing I can do. But this one, it can show it barely. But there's more digits. So what do? Well, your calculator can change if you do mode. And on the second row there, norm and psi, we want scientific notation. We press enter, and then we quit, and we're like, no, my number's gone. No, just press enter, and it'll come back. So that's not right. So we should call this 4.3 times 10 to the minus 9. Any questions? Yeah. How did I get it? What? Okay. From this, how do I get to here? Yeah. So you got one of these, right? So go up and press the mode button up at the top, and then move the cursor down to the second row. It's probably on norm. Move it to the right to psi, and press equals. And then quit, and press enter, and it'll show you that last value. Yeah. Yeah. The other thing you could do, like if you forget how to do that, the other thing you could do is you could say, well, I'm just going to multiply this by like 10,000. I know it's supposed to be 10 to the minus 9. I'm just going to multiply it by a big factor of 10 so that I can get this to move over and show me the other digits. That's kind of a cheat way of doing it. Any other questions? We only have 4 more slides. We're just going to finish it. So we saw this picture earlier. We've got POH. POH is just the negative log of the hydroxide ion concentration. So this P here is a mathematical operator, negative log. So instead of writing negative log, we write P. So pKa is the negative log of Ka. Px, whatever x could be calcium concentration or anything, is just the negative log of x. Derive the relationship between pH and POH. Which way do I want to go? I'm gonna do this one over here. So Kw, the ion product constant, equilibrium constant for water, is H plus times OH minus. I'm gonna take the log of both sides. And why would you randomly decide to do that? Well, it's not random. Actually, let's just take the negative log of both sides. If we take a logarithm of things that are multiplied, we can add the logarithms of each of them. And so negative log of hydrogen ion concentration plus negative log of hydroxide ion concentration equals negative log, that fell down, of Kw. What's another way of writing negative log of H plus? pH. And negative log of OH minus? POH. Here, Kw is 1.0 times 10 to the minus 14, right? So the negative log of that is what? 14. There it is. The POH added to the pH will always give you 14. Here in the middle, this plus this equals 14. Over here, this plus this, 14. Over here, this plus this, 14. Any questions? It's great if you understand how this works. Do you have to? No. You just need to know that pH plus POH is 14. And now we get to the circle of life, the circle of pH. So we've got a bunch of different things here that we've been talking about, and they're all related to each other. So we have pH. Let's see if I can do this well. And we've got POH, and we've got hydroxide, and we've got hydronium. Well, it's looking a little more like an oval of life, but you get the idea. So we can convert between pH and H+. It's not a very good arrow. We know that pH is negative log of H+, or going the other way, H+ is 10 to the minus pH. We can convert between hydrogen and hydroxide ion, because we know that if we multiply these, we get 10 to the minus 14. We can convert between POH and hydroxide using equations just like this. And the one we just learned, So you should be able to convert between any two things here. Like if you're going from pH to hydroxide ion concentration, there are two ways you can go. Is there a direct equation? Yeah, I'm sure there is. Do I remember what it is? Absolutely not. And do I care? No. Because I remember these other guys, and it's just two little steps. And you can go either direction, whichever makes more sense to you, whichever seems easier. I like this. This seems easier to me. The plus is equal to 14 rather than multiplying is 10 to the minus 14. So I would go this way. So you can go anywhere around the circle.
Is that supposed to be negative pH or negative pH?
Here?
No, on the bottom right here.
This?
Yeah, below where it says 10 to the power negative pH.
10 to the negative pH?
Is it supposed to be negative pH?
Thank you. No. We should, keep track of my mistakes. I think this would be a record. Thank you very much. One more slide and we'll be done. So as the pH of a solution increases, meaning the pH number gets higher, what happens to the acidity of the solution? It decreases. And that's one of those kind of opposite things that can be confusing. As the pH gets larger, pH 10, 12, 14, it becomes more basic, the acidity decreases.